Okay. Okay. So there's one announcement. Okay, so next week will be our week 14, which is the final week of the semester. Then during this week, I mean, of course, we have another topic to discuss during this week. And also I will discuss a bit, not discuss, I mean, I will just brief a bit about final exam during this week. Okay, and this is a physical in-person lecture, not online lecture, as you all know. Okay. Okay, so let's just recap a bit about what we did yesterday. So we did discuss about cylindrical coordinate. Okay, so just another way to describe uh, surface, or actually a point, okay, in 3 dimension, and then how we integrate during the, I mean, using this coordinate. Okay, so hang on. Okay. Okay. So, okay, so we discuss about this actually 6 basic uh, quantities. Actually, it's three basic quantities in uh, cylindrical coordinate, and each quantity is actually represent 2 walls for your wedge. Okay, you have the cylinder, vertical half planes, and horizontal planes. Okay, and this actually the difference between every quantities. For example, delta theta, which is the difference between the angle, is called the central angle, and for the r is thickness, and for the z is the height of the wedge. Okay, and then we derive. I mean, we don't really derive. I mean, we discuss about the limit of the Riemann sum, which is actually the triple integral over this um, G. Okay, I mean the solid G. Okay, and then uh, it's mentioned in the slide as shown here that the delta V is actually R, delta theta, delta Z. Okay, so you've seen this before, okay, which is from the polar coordinate. Okay, but now you have extra component or extra element or extra term, which is delta Z, which is the height, okay, which give you your integration must be r dz dr theta or any order of integration. I mean, it can be r dr theta dz. It's up to you. But it, I mean, if you change this order of the integration, of course, you need to change the limit, and that's why we write here appropriate limits. Okay, so this is at what we seen before in Cartesian or rectangular coordinate, in which if you try to integrate certain function f here, okay, let's say you are given certain function f, where f is a function of 3 variables, which is the r, the theta, and z, then integration of this f over solid G, which means what you see here is the domain of integration, then this triple integral can be decomposed into iterated integral, in which first you solve it. I mean, you do integration with respect to z, okay, where the lower limit is g1 here, and the upper limit is g2, which is the surface here, and followed by double integration over r. So since it's since this is r, then this is dE, which means that the formula here is the same for, I mean, it's similar for Cartesian and, I mean, rectangular or polar coordinate. Okay, so here dA means r dr d theta, and of course you can change the order of integration. Okay, so this is the usual theta, and this is r, and this actually comes from your region R here, which is the projection of the surface, sorry, projection of the solid G onto the XY plane. So you have this. Okay, but it's possible that the question give you different kind of solid or different kind of setup in which the projection is not on the XY plane, but on YZ plane or XZ plane. Okay, so in that case, you need to modify your integration. Okay, especially the limit. I mean, specifically the limit and also the dz and the r d theta. Okay, so you might have, I mean, dx dr theta, where r and theta is defined on y z plane, not on the xy plane. Okay, and then okay, so we discussed about this example. So we have, I mean, here we were not given f, which means that most possibly is a question for, I mean, to find volume, and actually it is, because here you are asked to find the volume, which means that your integrand is 1. Okay, so you have this. Okay, but of course you can rewrite this, and because it has 3-dimension or triple integral. Okay, you can do it in double integration. Okay, so let's say you have this, I'm sorry. Okay, let's say you are given this and you are asked to find the volume using double integration or double integral. Okay, so here, if you do double integration in polar coordinate, okay, so the volume is a double integral over r, and this is the integrand is the height, or the, I mean, specifically the difference between the height. So you have here the roof, which is the part of the, or portion of the hemisphere, which is 25 minus r squared, minus the floor, which is z equals to 0, and we have here r dr d theta. I mean, like, this is the dA. Okay, and this is actually equal to this. Okay, so this is by using double integration, where the roof and the wall, I mean the floor, is actually at the integrand, but for triple integration, the roof and the wall is not the wall, but the floor is actually at your limit of the z integration. Okay, so there is difference between them, but it's actually, it gives you the same answer, because I mean, after you solve this, you get this. Okay, but I mean, it depends. I mean, if the question asks you to do triple integration, then you need to do triple integration. But if it doesn't specify the type of integration, then you are free to use double integration, triple integration, or any coordinate system. Okay, and then there are other examples. Okay, I hope you try this. Okay, and the supplementary material. Okay, so let's go to the new slide. I mean, new topic, which is the spherical coordinate. Okay, so we've learned about, I mean, so we have triple integration or triple integral, sorry. So we learn about rectangular or Cartesian coordinate, and yesterday and just now we discussed about cylindrical coordinate. And now we want to discuss about spherical coordinate. Okay, I have uploaded this slide, I think 2 days ago. Okay, so these are the topics. Actually, this topic are similar to what we have for the other two coordinate system. Okay, so basically, I mean, here we have our point is described by the position x, y, z. Here, our points are described by r, theta, and z, where this z actually is same z. And here we have rho, theta, and phi, in which the this different color. The theta here and the theta here is actually the same. Okay, but the other two quantities are different. Okay, so triple integral involving sphere or cones. It's mentioned specifically here that if you have sphere or cones, I mean, if you have the triple integration or triple integral that involve these things or this shape, then it's often easier to evaluate or to solve when by converting your integral to spherical coordinate. Okay, so in spherical coordinate, the simplest equation are of the form, since we have these three quantities, the simplest, of course, by taking all these quantities to be constant. So here we have rho equals to certain constant, theta certain constant, and phi certain constant. Okay, so phi here is actually spelled by phi. Okay, phi. So for example, we can have rho equals to 3. Rho equals to 3 actually is a sphere with radius 3 and centered at the origin. Okay, so in Cartesian coordinate or rectangular coordinate, sphere is described by s squared plus y squared plus z squared equals to certain radius a, for example. Okay, I mean here sphere with center 0, 0, 0, and the radius, I mean I just use r equals to a. Okay, so here in Cartesian you use this equation. Okay, which is quite complicated, but I mean if you, I mean after some time, of course you remember this formula. Okay, in hang on, I shouldn't use this r equals to a, so I just write radius is a. Okay, so in cylinder or cylindrical coordinate, this is r squared plus z squared equals to a squared. So this is cylindrical coordinate. As I said, cylindrical coordinate is the extension of the polar coordinate to 3 dimension. Okay, and then as mentioned here, okay, for spherical coordinate, we just use rho equals to a, right, to describe sphere with center 0, 0, 0 and radius a. And the center is 3 component or 3 elements for the center because it's 3D. It's a sphere. There's x, y, z component. Okay, for a circle, there are only two components: the origin, which is cos 0, 0. Okay, because circle is two dimension shape. Okay, but for sphere is 3 dimension. That's why you have 0, 0, 0 for your center. Okay, here only rho equals to a. Okay, so here we will see why why we have this simple description of our sphere, and then we have another quantity which is theta. Okay, so if theta equals to constant, let's say theta equals to pi over 4, then it will represent actually a vertical half plane hinged on the z-axis with an angle pi over 4 from the xy plane. No, exact plane. Okay, so that we've seen, I mean, this is just this quantity that we've seen before. Okay, so it's a half plane. I mean, we discussed this yesterday. Okay, so it's actually same theta. So if we have theta equals to pi over 4, then we have something like this. I'm sorry if this is quite small, but I think you can see it from here. It's pi over 4, then we have the angle here, and then we have our plane, which starts from here, from the axis. I mean, it's actually extend until minus infinity, and I mean from minus infinity to positive infinity. But for the sake of visualizing this, so we just draw something like this. Okay, and it's hinged. I mean, it's attached at this z axis, and the angle is actually measured from the polar axis, which is, we can see, exact plane in this case. Okay, so the third, which is the phi, if it's equals to pi over 4, is actually the upper nape of a circular cone. I mean, this one. Okay, it's a circular cone. It's not like a pyramid. A pyramid is not circular cone. Okay, pyramid is like the tetrahedron. Okay, it's not circular. So it's a circular cone with its vertex at the origin, which is here. Okay, so just consider the upper nape, the upper portion of this cone, not this one, and here. Okay, and then hang on, and there is line of symmetry along the z-axis. I mean, this is the z-axis, and it's actually symmetry. Okay, rotational symmetry. I mean, symmetry. I mean, if you take the cross section of this circular cone, you see identical shape, which is symmetry along this axis. I mean, if you cut it with certain value of z, for example, z equals to 1, then you will see very identical rotational symmetry shape. And then the angle here, I mean, theta equals to pi, sorry, phi equals to pi over 4 is actually give you the angle between the surface of the nape and the z-axis. So you have this z-axis, and the angle between this, actually this, and or any value of theta is actually pi over 4. I mean, if I can write it something like this. Oh, hang on. I thought, sorry, I'll just take, oh, hang on, what happened? So I'll take this whole thing and put it here. Okay. So the angle, probably from here to here is phi, which is pi over 4. Not only here, but in any direction. Okay. Because these are 3-dimension kind of thing. Okay. Yeah. So we will discuss about this more. Okay, which is here. I mean, you can see it. So, or probably I can just hang on. Let me. Okay. So let me just keep this slide for a while. Okay. So I'll take this. Okay, and put it here because I need to just to write something on this. Let's say you are given certain point P. Okay, and then you know that it has coordinate in Cartesian equation. You can write it as, oh sorry, x, y, z. Okay, you have P x, y, z, n, which means that this is your x value, this is your y value, and this is your Z value. Okay, so this is for Cartesian. Okay, so for spherical, it's slightly different. I mean, it's different, not really slightly. Okay, because the way you describe this is by using theta, rho, and phi. Okay, you don't use x, y, and z. Rather, you use theta, rho, and phi. Okay? As you can see here, rho is the distance between point P to the pole, which is the origin. Okay? So you measure the distance between them. I mean, easy to calculate. I mean, if you have a point, then you can just calculate the magnitude to get its distance from the origin. Okay, so this is easy to calculate. Okay, so and then here you have the projection of this point theta. We give you point Q, where Q is, I can write it here. So Q is x, y, and 0 because it's on the xy plane. So it has 0 value in terms of z. And then from here, you draw a line and you calculate theta. And this is actually not new because we've seen this in cylindrical coordinate. Okay, so from there you get theta. Okay, so this is the first quantity. This is the second quantity, and the third is actually, it's like this one. It's like the theta, but it's measured differently. I mean, you have your P here. You don't need to project to any plane, but from P here, you draw. I mean, you have this line, and you just measure the angle from the positive z-axis to the line that connects the origin to P. And this is the third component, which is phi. Okay, so here, this is Cartesian or rectangular. And here you have rho, and this is P, this is rho, and theta, and phi, and this is spherical. Okay, and for cylindrical, this is the same point, but you take r, which is here, the distance, for the projected point Q, and theta, you take it from here, but you need z here. So this is for cylindrical. So Cartesian and cylindrical doesn't really, I mean, both of them are not much different, but spherical is probably something almost totally new. Okay, because you measured, I mean, you have two angles describing a point. And so you have rho, which is distance or magnitude, but now you have two angles describing a point. Okay, which is quite misalkan again, it's not really, it's like making things more complicated rather than simplifying things. But it's actually, as described in our first slide, this kind of coordinate system is expected to be useful when you have two things, spheres and cones. If you have like a rectangular box, then there's no point using spherical coordinate. Just use Cartesian or rectangular coordinate. Okay, so if you have sphere and cone, probably it's good, or probably consider to use spherical coordinate. Okay, then go back to the previous slide. Okay, let's say you have a spherical wedge. I mean, this is like the wedge that we seen before this for the cylindrical coordinate, something like this, or probably this, okay? But now, I'm sorry, I think this one, okay. But now we have spherical coordinate, I mean spherical wedge, okay? So as we discussed before this, I mean, in spherical code, in spherical coordinate, for spherical coordinate, there are also 6 quantities describing this wedge. Of course, is the quantity that we just discussed. Okay, so we have here wedge, and then there are row 1. Yeah, I mean, I'll just take this. Okay, and put it here and make it slightly bigger. Okay, here you have row 1. Okay, so as we learned before, row is actually represents sphere, right? So row 1 is actually this part. So this part actually is a small portion coming from a sphere with radius rho 1. And it's just a small portion from the sphere with radius rho 1. And then you have the second one, which is rho 2, okay? Where here rho 2 greater than rho 1. I mean, as you can see here. So here, it is here, it's actually here. So this is described by rho 2, which is the sphere with radius rho 2. Okay? And then you have theta 1. Okay, theta 1 is actually the angle here. And you go up here, and it's actually the part here. Okay, so the angle for this left surface of the spherical wedge is actually rho 1. Sorry, theta 1. And similarly, you have another surface, which is the right surface of the wedge, which is coming from theta 2. Because theta 2 is at here, and then the right surface actually, if you project it, you can see it's actually here. Okay, in here. And then the third one is that you have phi 1. Phi 1 is actually the surface here, okay, which is the top, the upper boundary of your wedge. And it's actually measured, if you measure the angle, it's actually give you the same constant, which is phi 1, okay? Whether here or whether here, it always give you phi 1, okay? And then you have another one. Oh, sorry, I forgot to mention that here, theta 1 is less than theta 2. I mean, similar to this. And then here, phi 1 is less than phi 2. So phi 2 represent the lower boundary of your wedge. Okay. I'm sorry if you can't really see it, but I think it's here. Okay. So this, of course, is a inclined plane, but it has constant value of angle if measured from the positive z-axis. Okay, so the angle is constant phi 2. But of course, I mean, it's not necessarily need to be constant, but in this case, we just discuss it, assuming that they are all constant. Okay. So the dimension of this spherical wedge is, I mean, is analogous to what we have for the cylindrical coordinate. So we have delta p, sorry, delta rho, not p, delta rho, which represent the difference between this, which is actually the difference between the magnitude or the distance between the inner and the outer boundary of the wedge. Okay? And then you have delta theta, which is what you've seen before, okay, which is the difference between this, and you have this, and then delta phi is the difference between the angle. So here, if we can write it, hang on, what color should I use? Yeah. This will be your delta phi. This should be your delta theta, and the distance between them, hang on, it should be from here to here, the theta. Okay, so here, I mean, if you take any points, I mean, for any value of r, delta theta always constant in this case. I mean, like, if you have something like this, okay, let's say this is your x and this is your y, and let's say your point is here, okay, the angle is theta. I mean, let's say this theta 1. But if you move this point to here, for example, I mean, now the point is closer to the origin, the angle always theta 1. It doesn't change as long as it lies on the same line. So, I mean, this is also true for this. Okay, so this is delta theta, this is delta theta, this is delta theta, and this is delta theta. Okay, so yeah, we can write the solid G as, so we have G, the rho theta phi, and then rho is between rho 1 and rho 2, theta between theta 1, theta 2, phi between phi 1 and phi 2. But sometimes I use it, I mean, I wrote it in different order. Sometimes I write, sorry, theta first, followed by rho and phi. Okay. So we discussed this just now. Okay. And then you can actually, I mean, if you have x, y, z, like this. Let's say you are given this. A certain point P is x, y, z coordinate. Okay? You can convert this x, y, z coordinate to the spherical coordinate, which is rho, theta, and phi. I mean, like if you use polar coordinate, for example, you know the relationship is x equals to r cos theta, y equals to r sin theta. Okay, and then which means that if you have x and y, you can get r and theta by solving this. And in addition, you know that x squared plus y squared equals to r squared. So you can easily convert x and y to r and theta. I mean, this is for polar coordinate. Okay, but now for rectangular coordinate, let's say x, y, z, you want to convert it to, I mean, this is rectangular. If you want to convert it to rho, theta, and phi, which is the spherical coordinate, it's not difficult. Okay, so here, I mean, this is actually this. Okay, but now we have more detail here. Okay? So this is, so we have this. Okay, so we start this here. We have the rho. Okay, and then you have the phi, we have the theta. Okay, so if this is rho, sorry, if this is phi, this is rho, then this must be rho cos phi, and this must be rho sin phi. Okay, so this and this is the same, rho sin phi. Okay, so I hope you understand this. I mean, this is purely taken from the definition of rho, phi, and theta. Okay, you get this. Okay, now consider this, the base of this, I mean, the triangle here on the xy plane, so which is this. Okay, so this is x, this is y. Okay, we know from polar coordinate that this is r and this is theta, which means that this is our x, which is r cos theta, and this is our y, which is r sine theta. Okay. Okay, so let me see. Okay, so from this, actually, we can get z equal to r cos theta. I mean, we start from here. No, not r cos theta, but rho cos phi. Okay, because this is rho, this is phi, which means that this is rho cos phi. So we have this, the third equation. Now we are left with x and y. We know that this is x, which is r cos theta, and this is y, which is r sine theta. Okay, so let's write this. I'll just take this and go to the next page. Here. Okay, so it's clear that we have z equals to rho cos phi. You need to remember this. I mean, you don't need to really memorize this, and because I even myself don't really. Sometimes I just don't really remember this. Okay, so you just need to know how it's derived. Okay, so it's obvious that z equals to rho cos phi, which comes from the definition. Now you need x. You know that in polar coordinate, x equals to r cos theta. Okay, what is r? R here is the diagonal, the hypotenuse. Okay, which is here, right? This is r from polar coordinate, and this is the length here is r from polar coordinate, but the length here defined by the definition of rho, theta, and phi is rho sine phi. So you just substitute. Okay, so you have here r equals to rho sine phi cos theta. Okay, so you have this. Rho sine phi cos theta. Similarly, for y, from coordinate, you have r sine theta, where r here is actually rho sine phi. So you just so you just substitute, and you get rho sine phi sine theta. Okay, which is here. So easy, right? Okay, and then note that if you square this quantity and you add them, you will get x squared plus y squared plus z squared equals to rho squared, which is not surprising because you know this from the Pythagorean theorem extended to 3 dimensions. Right? You have x squared, which is existent here, plus y squared, which is existent here. You get this, which is the hypotenuse, is z squared. And then z squared, you repeat the Pythagorean theorem, which is r squared plus z squared, and you get the distance here, which is rho squared. That's why you have this. Of course, you can use this mathematically to derive it, but from Pythagorean theorem, you know that if you have this kind of thing, then it straightforwardly give you this. Okay, so so you have this definition of triple integral in spherical coordinate. Okay, these are the limit. I hope you can read it yourself because I uploaded this 2 days ago. Okay, so it's actually similar to what we've seen before for other coordinate system. Okay, so you have this. but the one different thing is the delta V. So delta V equal to delta x, delta y, delta z for Cartesian or rectangular coordinate, or equal to delta, sorry, r, delta theta, delta z, or any order. I mean, they are just scalar, so multiply them doesn't change anything. So this is for cylindrical. But for spherical, it's slightly different because it's actually rho squared sine phi delta rho delta theta delta phi. Delta rho delta theta delta phi. Okay, so this is spherical. Okay, which means that if you have triple integral, let's say you are asked to do triple integration where f is function of 3 variables. So you have rho, theta, and phi. So this is g. So this is dv. So your dv is actually taken from here, which is here rho. I mean your f, rho theta, phi, and this is actually rho squared sine theta, and delta rho will be d rho, delta theta will be d theta, and delta phi will be d phi. And here you have appropriate limits in which this, because this is rho, then this must be rho. So I just write rho 1, rho 2. And this is theta, which means you have theta 1, theta 2. Theta 1, theta 2 could be constant or function. And here phi 1 and phi 2. Okay, so I just write here appropriate limits. But of course, the outer, the limits of the outmost integral must be constant. Otherwise, you won't be able to solve this. Okay, so this is appropriate limits. And of course, you can change, I mean, to any appropriate orders. And you can change them, which means that here, the rho squared sine phi is part of your integral. Okay, so now you have extra term for your integration. Okay, so determining limits of integration in spherical coordinate. So let's say, how many minutes we have? Like 10 minutes. Okay, suppose that we want to integrate. We are given certain function f. Right? We don't know what the function actually is, but we want to integrate this f over the integration, our domain, which is the solid. Okay? Here, the solid here is our domain, not our function or other things. Okay, so we want to integrate f over the spherical solid G. The spherical solid G is actually all points here contained by the sphere with radius rho naught or rho 0. Okay? So you want to include everything, every point inside this for your integration. This means that the sphere is just cover or the surface of our solid or our domain that we need to take into account all points inside it for our integration. Okay, so there are 3 steps, okay, which are suggested for our integration. So step 1. Okay, so assuming that, hang on, I'll just go back here. Here I write, okay, in our example, usually we we do something like this: d rho, d theta, d phi. And we start with integration with respect to rho, followed by theta, and followed by phi. And we will use this order of integration for probably all our example. Okay, but of course we can change if we want. So in this case, we'll start with rho first, which means that if you want to integrate with respect to rho, we need to fix or assume that theta and phi are constant. So we fix them. Okay? So we let rho to vary, to change from 0 to from 0 to rho naught or rho 0. Okay? So this actually gives us the line or the radial line from the origin to the surface of the field, because by definition, rho is the line here. So we consider rho from 0 to the end here, which is rho naught. So that's why we have this line. Okay, so now settle with 1, which means that we can write, okay, so we have our rho from 0 to, to rho naught. Now we want to decide the limits for theta. So what we are going to do is that, hang on, no, I think rather than doing this, I mean, because the example was taken from the book, so I just follow their picture here. So no, rather than we do this, now we change it slightly differently. I mean, here we do d phi, d theta. So, okay, so so now, I mean, example 1 will be based on this, which means that now we need to decide on phi. Okay, so we have our line here, the radial line originating from the origin. Okay, now we keep theta fixed. I mean, we don't consider theta. We just let phi to vary from 0 to phi. Sorry, to pi. Sorry. Okay, so we get something like this, a fan-shaped region. I mean, we take this line, we move it from theta equals to 0, sorry, from phi equals to 0 until phi equals to pi. Okay, so I just take this edit selection. Oh, sorry, what happened? Okay, yeah. Okay, so just now we have this line, the radial line, and now you move it, or you can move it to the left or to, I mean, to move it up or down. Okay, so the angle here, I just use red color, I'll put it black. This is phi equals to 0. Remember, phi is measured from the positive z-axis. Okay? So here, phi equals 0. And then you move this line, or you move it down until here. Okay? So the angle is measured from positive z-axis, which gives you phi equals to pi. Okay? So it's measured from here. Okay, that's why you get 0 to pi, which means that here you have 0 to pi. Now you have this like half of a disk. Sorry, yeah, half of this. Okay? Okay, you don't move. I mean, of course, you can move it until, if you move it, let's say, until from 0 to 2 pi, you get a full circle, something like this. Can, a full disk. Okay, but in this case, you don't consider it. I mean, you just take half of, half of this. Okay, just, just for the sake of using this example. Then what you are going to do is that you need to find the limit for theta. Okay, So you have this, you can move it. I mean, from here, I mean, in this direction or in counterclockwise direction. Okay, let's say you move it in the counterclockwise direction. I mean, um, avoiding this axis. I mean, you try to make to distance the angle from the positive axis. I mean, you move to this direction. Okay, so this fan shaped region, which is this the disk here, will make a complete revolution, thereby sweeping out the entire sphere. Okay, we can imagine it. I mean, like from a line, which is a line that just a simple thing, 1D, you form a half disk here, or fan-shaped region, what we call it here. And once you have this, you move it. You move it in counterclockwise direction for angle 2 pi, which means from 0 to 2 pi, and you get this complete revolution. Or in other words, you have your sphere. So here theta is from 0 to 2 pi. Okay. So hang on. So let's say you want to do something, I mean, slightly different. I mean, of course, you take rho from 0 to rho 0, but now your theta is something like this. I mean, you have a full disk, not only this part, but also the other part, okay, which is this. Which means that now your phi is from 0 to 2 pi. Because phi is measured or is calculated from the positive z-axis, which is from here, and then you move it not only here, but to this. That's why you have phi equals to 2 pi. Okay, so in order to get a complete revolution, when you have a disk, you just need to rotate it for pi angle or pi degree, which means that in order to produce a sphere, or all points in the sphere, your theta must be from 0 to pi. Okay? Because the one region, I mean, if you have this, one region here will be covered by the one portion of the disk, and the other region here will be covered by the other portion of the disk. Okay? It's like, I don't know how to mention it. Probably, if you have, I mean, you can imagine, okay, let's say you have something like this line. Okay, so I asked you to cover the whole thing, so you just need to rotate this going to here, oh sorry, this going to here for pi, for I mean angle pi, and then if you move this, okay, I mean they both move. Okay, so you just need pi to complete the revolution. Okay, because the region here will be covered by this line, and the region here, okay, will be covered by, oh sorry, by this line. Okay, so if you have a line which extend to both direction, so you just need angle pi to produce a complete revolution. Okay, but of course, if you have like something like this, of course you need to rotate it for 2 pi in order to have complete revolution. But if you have both both lines here, then we just need pi. So it's, I mean, it's similar to what we have here. If you decide to have a full diff, then your theta will be from 0 to pi. So you choose whether you want this to be pi or 2 pi, then this angle or the upper boundary for the theta will be changed accordingly. Okay, so time's up. Sorry, because we had just exceed 1 minute from the actual time. Okay, so please have a look at this example. I mean, there are a lot of examples here. Okay, please try to understand every single of one of them. Okay, because I mean, here you don't do the integration, you just discuss how to get the limit. And also this, and also this. Please try to understand them, and then try to do this example, example 7, example 7, example 9, example 10, example 11, example 12, and supplementary material. Please read through all this material, and then we will discuss this after next week on Monday and Tuesday. And of course, we have another topic, which is the what is it? The change of variable. Okay, so I think that's all. I mean, you may leave if you need to. Okay, but if you have question, you can ask now. That's all. Anyone has any question? Oh, sorry.
Dr. Ni last topic.
No. We have another one. Okay, which is change of variable. I think we should be able to finish everything next week.
Okay. And then yang masuk final daripada lepas mid-sem hari tu kan?
Yes, I mean all my parts will be included in the exam. Today's topic, next week's topic. Okay? Boleh?
Okay.
Sorry, yes, but there's an international student, so I need to answer in English. Yeah. So is there any other question? Okay, if you have a question, of course you can, I mean, you can email me, or otherwise you can meet me next week. I mean, the office hour, okay, on Thursday. Okay, so if there's no question, I would like to ask, not ask, I would like to wish Selamat Hari Raya, okay, to everyone. And happy holiday to everyone. I mean, who not celebrating Hari Raya. Okay, so I'll see you next week. Thank you.
Thank you, Doctor. Thank you, Doctor.
Thank you, Doctor.
Thank you.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.